Hello there, I'm Thomas. Hatsios, the British American pilot flying the Boeing 777-300 ER-89 flight from Zurich International Airport. We're going to be flying Zurich, Switzerland, Germany, and then coming back to the Zurich International Airport. Runway 1449, let's localize and landing. So now I'm in the cockpit for the takeoff preparation of the Boeing 777-300 ERX of the PMDG simulation and Microsoft Flight Simulator 8. So I'm gonna start showing you the cockpit instruments of the Boeing 777-300 ER airplane. I'm gonna start with the primary flight display, show you the airspeed indicator, the minimum speed indicated, the ground speed, the target airspeed, the barometric altitude above the sea level, the target altitude selected from the autopilot and flight director system panel, the AFTS, the radio altitude above the ground level, the rate of climb and descent of the aircraft in tens, hundreds and thousands of feet per minute. Also the barometric pressure of the outside atmosphere. We have the magnetic North Pole, or the true North Pole, and the magnetic variation depending on where we are in the world. We have also the magnetic heading and track. We have the altitude indicator with the pitch ladder in decrease and the bank angle in decrease. Also we have the Lszh localizer crossbars and the flight director crossbars for manual guidance, or the autopilot crossbars for automatic guidance of the aircraft. We have also the bank angle of the aircraft and the angle of attack, and the pitch ladder in decrease, 2.5 degrees peak marks. For the pitch ladder, we have also the flight mode annunciator with the autopilot and auto throttle later and vertical navigation modes. We have the navigation display that displays the airports, the waypoints, the navigation aids. We have the GPS map display from the weather radar that displays also the terrain reflections. So you can see the terrain with red, yellow, and green. Also you can see the lakes, the rivers, the sea, and also we can see things like the mountains and the ridges in the ground. We have the heading of the aircraft, magnetic North Pole or true North Pole again, and magnetic variation depending on where we are in the world. We have the GPS position, the inertial GPS position, the RMP and the AMP, the required navigation performance and the acquired navigation performance. We have the wind direction and airspeed. The next waypoint we're going to be overflying. Also we have the display of other aircraft flying around our own aircraft using the transponder, the ATSP and ATSC transponder, transmitter and receiver that transmits our own position, altitude and direction, and also receives from other aircraft or transmits to the air traffic control tower. So we have also the flight management computer. We're going to use it for input the aircraft weight for takeoff. Also other information about the airport where we are located, the departure airport, runway, the destination airport and runway, the intermediate waypoints, navigation fixes, the suites, the start arrangement, departure, then the start, the start terminal arrival, and also we're going to have a destination airport and runway. And we're going to create a flight plan using the flight management computer, a complete flight route, horizontal and vertical guidance profile. This is going to be interconnected also with the autopilot and flight director system panel, and the auto throttle and the auto trim system of the horizontal tail trim stabilizer that utilizes the auto trim function. So we're gonna have the flight director, autopilot, flight controls. So it's gonna be I'm gonna show you how to use it to navigate the aircraft in flight. Also after that I'm gonna come to the autopilot and flight director system panel, the AFTS that contains the auto throttle left and auto throttle right engage and disengage switches, the autopilot on and off engage and disengage switch, the flight director engage and disengage switch. We have the airspeed select node. We can select an airspeed, target airspeed, and the auto throttle is going to give a signal to the FADECs. The FADECs are the full authority digital electronic control computers that control the engine's functions. We have the turbofan turbojet G90 General Electric 90 installed in our Boeing 777-300 ER one in the left wing and one in the right wing for asymmetrical thrust and redundancy. So I'm going to explain you later the function of the FATEX and how it's interconnected with the autopilot and autothrottle and also the flight management computer. Or you can utilize it by moving the thrust levers manually. So we selected the airspeed in the autopilot flight director system panel. Then we have some modes like continuous thrust mode or fixed thrust mode and variable thrust mode. So we have for climb, for takeoff and climb, the maximum continuous thrust takeoff ground, and then the climb continues. Then we have also idle thrust for descent, which is also a fixed thrust mode. Then for cruise and for approach and landing we have the variable thrust mode. So we indicate we will select a target airspeed in nautical miles per hour, knots, like 200, 300 knots, nautical miles per hour, or Mach speed, like 0.7, 0.8 Mach in cruising altitude. So we're gonna select modes like the auto throttle hold with the speed mode, also the climb continues and the flight level change. And then I'm gonna show you the LNAV and the VNAV, the lateral navigation, the vertical navigation modes. So we're gonna have an hour and 9 minutes left for this flight. Video length. So you're gonna see also the LNAV and the VNAV, the lateral navigation, the vertical navigation modes of the autopilot flight director system panel. We're gonna have also the banner angle select mid, banner angle select knob, and also the heading select knob and the heading hold switch. We have the vertical rate of climb and descent of the aircraft. You can select how fast the aircraft will climb and descend in a vertical rate profile, and using the slider and then adjusting the slider and then hitting the hold switch for this mode. We have also the altitude select knob and the altitude hold switch and the vol localizer with the approach for the autoland. So we have the Lszh localizer in the vol switch in the autopilot flight rotation panel, and we have the approach for the autoland function of the Boeing 777-300ER. Then I'm gonna come to the thrust levers, show you how to use the thrust levers, how to modify actually the thrust produced from the engines, so we will find turbojet engines. Then I'm gonna come to the flight theory of the aircraft, explain you about the takeoff speed. Then I'm gonna show you the flight controls. Then I'll show you the overhead panel, the electrical, the left and the right engine drive and integrated drive generators. The APU, the exterior power unit we're gonna use for starting the engines, also the batteries, the standard battery in the APU battery, the primary flight control computers, the ADIRU, the air data user reference unit. Also we have the hydraulic pumps, the left and the right engine driving, and the backup C1 and C2 electrical, which are also pressurized by the air system. Also we have other systems like the electronic engine control for the engines, the EC, the auto start system. I'm gonna show you also the fuel tanks, the left and the right wing fuel tank, the center tank, the forward and the aft pumps. I'm gonna show you the wing and engine radius. I'm gonna show you the cabin pressurization system and also the bleeder from the left and the right engine and from the APU. I'm gonna show you how to use these functions of the aircraft. So I'm gonna show you also the flaps and the slab system with the flight controls. I'm gonna show you how to use the flight management computer, the FMC, and I'm gonna make an engine start demonstration. So thank you very much one more time for joining me. I'm Thomas Hatsios, the British American pilot of the United States Air Force, flying the Boeing 777-300ER in tonight's flight. I'm gonna start now with the showing you the cockpit and the instruments. So you can see here, as you can see, so you can see inside the cockpit all the instruments, the flight controls, the yoke and the control wheel, the rudder pedals here. We have the steering control tiller for the nose wheel. The thrust levers here, the speed brakes retract automatically when we move the thrust levers forward. Also the flaps here, I will show you later how to use the flaps. Also the flaps here displayed. So we have the primary flight display that displays the airspeed indicated 30 knots. We have the target airspeed display with purples from the autopilot and flight director system panel. The ground speed is 0, so the aircraft is not moving right now. This is the parking brakes on. We have the barometric altitude above the sea level is 1430 feet. The target altitude selected from the autopilot flight director system panel 10,000 feet. The magnetic heading or track magnetic north pole and true north pole. The barometric altitude above the sea level. The barometric pressure of the outside atmosphere. The radio altitude here is 2 feet above the ground level. So we have the pitch ladder here and decrease the altitude indicator that displays the sky and the horizon over here on the ground. So you have the pitch ladder, you can see 2.5 degrees, 5, 7.5, 10, 12.5, 15, 17.5, 30 degrees climb or descend. The bang angle was like 45, 30, 25, whatever. So you can see the rate of climb, the tick marks here, and here is the airspeed, very important to remember. We're gonna have also, you can see the crossbars is the purple is the autopilot or the flight director. So you can see here this state is the rate of climb descent of the aircraft. Besides to the right side of the altitude, so you can see the needle moving up. The aircraft is climbing, or the needle is moving down, the aircraft is descending. So you know if the aircraft climbs or descends by looking at this needle here, not actually the pitch ladder, because it might be confusing for you. The aircraft might be pitching up and actually descending, so you have to know the rate of climb descent. This is the FS panel. I will set inches of mercury or hectopascals, and also we will display the meters. We can adjust also other things like the range here using these switches. You will see the radar scan here now. Different range, more or less, nautical miles, the distance here. So you can see here we have the takeoff ground arm in the flight mode annunciator. Over here, now we have also the display of meters for the altitude, 30,000, 3,050 meters or 10,000 feet, and here is 436 meters or 1,430 feet above the sea level. This is also the ground level, not changing, the same display feet. So we have inches of mercury. Now we have hectopascals. 1013 hectopascals as the standard barometric. Magnetic here, we can change magnetic here, north or true north over here. Now we have the true north heading reference, so we can find the north pole or the geographic north pole like this. The magnetic or the geographic, it has some small difference depending where you fly. So you can see the true now displayed over here. We will set magnetic normal again. We will display magnetic here, and magnetic also, magnetic north pole over here. So you can see the terrain. You can see the terrain map over here. The altitude is 6,100 feet. 0 feet also, so you can see the red is the maximum right now is 6,100. The intermediate is the yellow, and the green is the 0 feet. You can see also the sea and the lakes, the rivers. So this is generally speaking is the blue is the airports. You can see like the Lszh here, the names. You can change other navigation also. So we have the distance 160 nautical miles, 320. The intermediate is 80, half of that is 40, So you can navigate. We have also other aircraft flying around us, displayed using. So you can see here is the weather radar over here with the terrain reflections, and this is a transporter, the DSP and ETC. We can test the transporter, see it is working. So you will see here it generates a warning for other aircraft incoming. So we'll say it again, inches of Mercury. We can now start showing you the autopilot flight director system panel. We have the upper and the lower ACAS. So we have 16. We have about 1 hour left for this flight. So we need to be a little bit more brief. You can see the overhead panel, all the systems. You can see here is the electrical system, the hydraulic, the ADIRU, the air data analyzer reference unit, the flight control computers, the windshield wipers, the lighting of the aircraft, the wing and engine radii. This is the hydraulic pumps I told you. So this is the left engine driving and this is the right engine driving. Generators, the backup generators here, the batteries. I'm gonna show you the FATEX, left and right engine. The electronic engine control for the engines, also the auto start system, and the fuel system here, the fuel pumps and fuel tanks. Forward and aft, the cabin pressurization and the bleeder over here. I'm gonna come later. So I'm gonna come here. To the autopilot and flight director system panel. We have the auto throttle left and auto throttle right. So auto throttle left on and off, flight director on and off like this. So you can see the auto throttle left here. It will display in the upper ACAS. Auto throttle left is off, the yellow. We have also the auto throttle right off and auto throttle left arm. It will display auto throttle right off. So we have indicator airspeed or Mach. You can set like this, flight level change. We have the auto throttle here. The climb continues, the auto thrust. So you can see the switches. Climb continues. This is the press balls where you can press in. We have the LNAV and the VNAV like this. We have also, this is interconnected to the flight management computer over here. This mode you can see here. So we will input later the data of the aircraft, and it's gonna interconnect this modes, the LNAV and the VNAV. We have the heading track, bank angle limit also select, heading. Vertical speed or flight path angle, altitude, select the target altitude. So I will show you now the altitude now, 35,000, and the target airspeed. You can see we have inches of Mercury, so the airspeed now, the target is 253 knots over here, nautical miles per hour. After takeoff, and the target altitude is 7,710 10 meters or 25,300 feet. around now 1430. So we have the magnetic heading also set 136 degrees. So a couple more modes we can tweak, like flight path angle, vertical speed. So you can see the minus here is negative, so it's descent. Now I'm gonna come to the plus, it's gonna be a climb. So you will see plus 3.5 degrees for this mode, which interconnects with the other, the flight path angle. So you will see the flight path angle after takeoff to 3.5 degrees, which generally speaking the same like the other modes for after takeoff pitch. And the pitch ladder, we can set maybe the autopilot also to be on, like this. You will see green here and green here, and also the autopilot display is on right now, so it's displaying the green light. Also heading for flight path angle, no difference to that. Now I'm gonna set the other mode, vertical speed of flight path angle. So now we have vertical speed 10,000 feet per minute. You can see the minus here. Now I'm gonna set the plus for climb 3,500 feet. You can see the slider, you can adjust how much you want to change the climb or the descent. So you have 25,300, and we have like a few more minutes for this flight. So vertical speed, flight path angle. Now we can set flight level change again, maybe later with the autopilot. Maybe we can disconnect also flight level change. You will see flight level change speed, heading hold with the autopilot, and also altitude hold for after takeoff. So we'll give you a different kind of mode. This is also autopilot disengaged right now. So I will press this switch out, it will disengage the autopilot like this. Rearm it, press it again, so you will see the warning here, the red. And here is the autopilot disengage. Here and here autopilot disconnect, so you take manual. Flight, you have no autopilot, you have flight directors here. So you reset. One more time now. I'm gonna use this switch here. So this is the autopilot disengage switch. You press. This is the horizontal tail. Trim stabilizer is different. So this is the control wheel. You rearm again. So you have the autopilot disconnect like this. The red. So confirm the disconnect action. So we have like maybe 35 more minutes for this flight to complete. We can see we have traffic here. Is another aircraft coming here. So it's in front of us. It's about to land. So we can see an aircraft coming to land in front of us. It says plus 100. So maybe it just went through. Let's see. No display. So again, access data. We have the terrain scan again. So now I'm gonna come to the thrust levers. I will explain you the function of the thrust levers, then the overhead panel. So you can see we can adjust the thrust here just by moving the thrust levers like that, forward or aft to the idle position. You can see the speed brakes are retracted automatically because this is just a speed brake, as you can read here. This is the trim. So the trim for the horizontal tail. So this is also the autopilot disconnect, the auto throttle disconnect, excuse me. So you disconnect the auto throttle like this. This is the takeoff ground. You press it and it arms takeoff. So you need to press again the other throttle disengage, and it will disarm like this. Speed brakes again. This is also another function of the thrust reverse. If you move up this handle, so it will reverse the thrust. You will see the rotation speed of the engines, and the thrust reverses open the blocker doors, so it reverses the flow of air from the bypass of the engine here. So you can see also the speed brakes extend automatically. For this function, when you land, you can also cancel this, retract, rearm the thrust reverse. Also see the other, the front side of the fan, so you can just see, you can cancel this, you can rearm. You will see the blocker doors here and here open when you activate the thrust reverse. So this is the thrust reverse. We cancel the thrust reverse like this. So we have the parking brakes, the horizontal tail trim stabilizer, the fuel control for the engines, left engine, right engine, fuel control switches, the stabilizer trim, the cutout switch for the horizontal tail, the C and the R. So if you have a malfunction of the C or the R hydraulic system, which drives the auto trim function for the autopilot and the auto throttle, you disengage from the normal to cutout, so you only have the manual trim. Here you can see the trim position of the horizontal tail, pitch up, nose pitch up, or nose pitch down, and the request. Also you can use the normal and the alternate pitch trim, or use this for pitching up and pitching down the horizontal tail. We have also the aileron trim here. You can see the position, and now the rudder trim here. So you have the rudder trim here, vertical stabilizer, and the aileron trim switches here. So this is the radio and communication panel. So now I'm gonna come back to the thrust levers. I will show you here. You can see here is displayed from the FADEX, the full authority digital electronic control computers. I will talk to you now. It's the N1, which is low speed, low pressure. The low speed starter in shaft, the low pressure compressor and turbine of the turbofan turbocharged engine, left and right. You can see the green is maximum continuous thrust or takeoff program, maximum takeoff thrust. You can see also red and yellow, never exceed limits, the temperature, just gas temperature, left and right engine. This is some warnings from other systems or the engines, the landing gear up and down, the flaps position, not related to anything, the bleed air from the engine. Also supplies the cabin pressurization system, the total of fuel on board in thousands of pounds. You can see the trademark of our aircraft right now, Boeing 777, the M2, which is the high speed starter and shaft, the high pressure compressor and turbine of the turbofan turbocharged engine, the fuel flow per engine per hour, the oil pressure, oil temperature, oil quantity, and the vibration of the M2 states of the engine. So we have the thrust levers here. You can adjust the thrust, you can move them forward like this. You will see the speed brakes again, retract. You can adjust a differential thrust like this. You will see different kind of display, more thrust in that, less in that. This is stuck. Now we're gonna do the opposite. Gonna move back to the idle. So now we're gonna adjust this side. to the forward differential thrust. So now you will see the other side engine having got more thrust while the other is in idle. You'll see the difference. You can also use maximum takeoff thrust like this. You'll see both engines moving up. You can see the limits also, quite short. So I'm gonna come now start the explanations of the engines, and we have less than 20 minutes for this, 25 maybe minutes for doing this video before anything start demonstration. So we have this thrust levers explanation. You can see we have one engine installed, turbo fan turbojet engine. We have the General Electric 90 G90 turbo fan turbojet engines, one installed in the left wing, one in the right wing for symmetrical thrust and redundancy. So we can use the thrust levers to adjust the engine thrust. We can modify the thrust, also connects with the autopilot as well as you and the flight director and the flight management computer. Modes the LNAV and the VNAV, the lateral navigation, vertical navigation. So you request target airspeed, and this is gonna generate thrust request depending if we climb or we descend, like maximum climb thrust or idle thrust for descent. So we're gonna have also cruise and approach and landing. So we have the FADEX, one installed per engine in the gearbox, receives also torque from horizontal torque movement. Also this generates the electromagnetic alternators of the FADEX for starting the FADEX function. After that, the FADEX are self-contained in terms of electricity. So the FADEX are installed, one in the left wing and one in the right wing, are the full authority digital electronic control computers that control the engine's functions. So it controls and monitors and displays the N1, which is the low speed starter and shaft, the low pressure compressor and turbine of the turbofan turbojet engines, the exhaust gas temperature per engine, the outflow air pressure from the engines. We have also this from the 5th and the 9th stage of the blade stages of the engines. Also we have the N2, which is the high speed starter and shaft, high pressure compressor and turbine of the turbofan turbojet engine. We have the fuel flow per engine per hour, the oil pressure, oil quantity, oil temperature, and the vibration of the N2 stage of the engine. Also the FADEX control and monitor the engine start, engine shutdown, engine's malfunction, the fuel flow rate to the engines. Also the pressure inside the engines, they regulate the outflow valves, the 5th and 9th stage. So we have another pressure inside the engine that cause the outflow valves into a lower stage to increase the pressure inside the engine. We have an overpressure, they open it up into a higher stage, so they relieve the outflow pressure from inside the engine. This is also necessary as we climb to higher altitudes. We have lower pressure, atmospheric pressure, and also we have lower oxygen levels and lower temperature. Also the aircraft flies much faster, so the intake of the air is of the air mass from the engine's front stage is much faster rate. So we have different cabin, we have different atmospheric pressures as we climb or as we descend, and also temperature and oxygen level and rate of intake from the front fan stage, which is admitted into the cabin, into the turbine compressor for compression and for fuel air mixture. So the FADEX adjusts also the fuel air mixture ratio. So instead of doing this manually like you do in the Cessna Skyhawk or whatever else piston or turboprop aircraft, you do this automatically by using the FADEX, the full authority electronic control computers that you have installed into your Boeing or Airbus airplane, or whatever jetliner utilizes this function. So so you have an automatic fuel air mixture all the time, also fuel optimization, efficiency and safety. So it's a good thing to have the Flught installed into your engine. Now I'm gonna talk to you about the flight theory of the airplane, explain you we're gonna input the takeoff weight of the aircraft, the fuel on board, the passengers and the cargo weight, and this is gonna calculate using the flight management computers automatically the takeoff speeds, the V1, V8 and V2. So we're gonna have also the flaps inserted for takeoff, 15 degrees of flaps and 4 degrees of horizontal tail trim stabilizer. So for this aircraft right now, the Boeing 777-300ER, with this weight right now, we have 254,000 kilograms of takeoff weight, which is below the maximum takeoff weight, or 531,000 pounds. So we have about 46,000 kilograms, or 102,000 pounds of fuel on board. It's only 30% of the total fuel the aircraft can take for maximum takeoff weight. Also we have about 46,000 pounds or 30,000 kilograms of passenger cargo on board. So in total we have 254,000 kilograms or 531,000 pounds below the maximum takeoff weight. As I told you, we're gonna use 15 degrees of flaps and 4 degrees of horizontal tail trim stabilizer. We're gonna utilize the runway 14 in Zurich International Airport, so we're gonna insert that also in the flight management computer. Has stored information about the runway length and other conditions. We're gonna see the temperature of the air and the atmospheric pressure, the altitude above the sea level, other factors like the wind speed direction and the runway conditions, like it's wet or ice, so or dry. So we're gonna have the takeoff speeds calculated, and we're gonna need for this configuration 254,000 kilograms, so 521,000 pounds. We're gonna need 15 degrees of flaps, 4 degrees horizontal trim stabilizer, and we're gonna need to accelerate to a takeoff speed of 154 nautical miles per hour, 154 knots, or 270 kilometers an hour. Just for takeoff, we're gonna need to overcome the stall speed of the wings of the aircraft. The stall speed is the speed at which the wings will not generate the necessary lift force. So we're gonna need, as you can see here, so we're gonna need to take off with the effective lift component from the wings. It's gonna generate enough lift. The lift must be equal to the aircraft weight, that is equal to the mass of the aircraft, and the acceleration of the Earth's gravity, depending on where we are in the world. So we're gonna have also that. We're gonna generate the flight conditions. I'm gonna show you also. I'm gonna start now explaining you about the flight theory of the aircraft. I'm going to tell you about the Newton's first, second, and third law of kinematics of motion, about the Bernoulli theory of fluid, and also aeronautical and aerospace engineering. So you how the aircraft is gonna develop the wings lift force. So by using the wings shape, and also the airstream, the airflow from the air mass as it accelerates to the takeoff speed and to the flight speed. So we need to overcome the stall speed all the time as we fly. So we have about 30 more minutes before we're gonna start the takeoff. So you can see here we have the aircraft wings. You can see they hold the mass of the aircraft. In total, you can see also the jet engines, the turbofan engine we have installed in the left and right wing. Also accelerate the aircraft, will generate the necessary propulsion by ejecting the compressor from their exhaust. So they can only move the aircraft forward. As you can see the vectors where the engines are placed over here. So we have the left and the right wing. You can see the vectors from the engines. You can see the wing shape. It holds the total weight of the aircraft. Also, you can see we have the mean aerodynamic chord position. Here is about 35% of the Mach. Mean aerodynamic chord is also the position of the maximum aerodynamic lift generated aerodynamic pressure of the wings. Also the position where the stall begins, the airflow becomes detached from the wings. You can see we have the leading edge here and the trailing edge of the wings. We have the flaps extended, also the spirit brakes, air spoilers up and down. So you can see the bottom surface of the wing. So I'm gonna start also with the center of gravity here. So you can see the position of the mean aerodynamic chord of 25% is also the position where the center of gravity of an airline or aircraft is being positioned. Is mostly symmetrical to its shape and weight. So you can shift the center of gravity forward or aft by moving passenger, cargo and fuel around the aircraft. So you can see here is the center of gravity, pretty much approximated. It's also the vectors. You can see the longitudinal vector, nose to tail, the wingtip to wingtip vector, the lateral vector, and the vertical vector is the center of gravity here. Also you have some forces from the horizontal tail. You have the lever arm or the pitch arm. So you can see lever arm is times, I'm gonna explain it later. Also some other forces, moment arm and moment, as they call them in aeronautical engineering. So you can see the bottom surface of the wing is more flat, generally speaking. So as the aircraft accelerates forward, the airflow of the air mass moves slower below the wing because the wing is more flat, so it pressurizes the aircraft wings up into the air. You have positive air pressure, higher air pressure below the wing, pressurizes the aircraft weight up into the air. Also the top surface of the wings is more flat, it's more curved from the top surface. So you can see the airflow of the air mass as the aircraft accelerates to the takeoff speed. It's moving faster above the wings, so we have lower air pressure above the wings. This creates an air suction above the wings, which sucks the aircraft up into the air. So you have negative air pressure above the wings. So you have more pressure that pressurizes the aircraft up into the air and less pressure above the wing. So this is the differential pressure between the bottom and the top surface of the wings. Also you have you can see the lever arms here. This times the distance from the center of gravity all the way back to the horizontal tail over the surface area of the horizontal tail or the elevator. So this times also the airflow of the air mass per second times the acceleration of the air gravity. Or you can utilize the vertical stabilizer as a vector from physics, Newton's physics, and Bernoulli theory of fluids. So we have the horizontal component times the distance from the center of gravity all the way over the surface area of the horizontal or the vertical tail times the airflow of the air mass per second times the acceleration of the air gravity. We have the lever arm or moment arm, and you can utilize any control surface for deflecting the airflow of the air mass. So you can make turns left and right, climb, descend. So this is the general explanation of the aeronautical theory. Now I'm gonna come inside the cockpit, show you the flight control. So we have not much time left for this flight. We have like 13 more minutes. I'm gonna start showing you the flight controls inside the cockpit that I'm utilizing. The side stick in my computer to control the yoke and the control wheel and the rudder pedals and the steering, the tiller of the nose wheel steering. So I have full control for flight controls. I have the horizontal tail trim stabilizer and the flaps in front. So I'm gonna come now to this competition here. I'm gonna show you. You can see here we have the side stick here. As you can see, I can pitch up and pitch down, glide or descend, bang roll left and bang roll right. Also the rudder pedals for turning left and turning right. So you can see the two control columns are interconnected where you climb or descend and bang roll left and right. So you have side stick deflection proportional to the control flight control yoke of the Boeing 777. As you can see, you can hold neutral, you can use the horizontal rotate stabilizer here. So this is how you control the airplane. If you have full flight controls or deflection like this, as like in the Airbus. You can also use, this is the thrust levers here, up and down, the horizontal tail trim, stabilizer over here, pitch up and pitch down, the tail of the aircraft. So you have full flight controls. You can see the size of the deflection is proportional to the control yoke. Now I'm gonna come in the outside view. I'll show you the same explanation again one more time. So you can see the outside view of the airplane. I extend the speed brakes and you can see I'm gonna show you how to control the flight controls from the outside view using the side stick of my computer, the Lszh constraint 3D. So you can see here we have the side stick deflections again. Maybe I need a more close-up view so you can climb, you can descend, you can bang roll left and bang roll right like this. You can see some delay maybe. Also the rudder pedals left and right and horizontal rotate trim stabilizer. So you can see the size of deflection proportional to the control the flight control surfaces deflection. So now I'm gonna come in the overhead panel inside the cockpit and show you how to start the engine. So make an engine start demonstration. I'm gonna show you how to start the APU and then set up the flight management computer for takeoff. So we have 10 more minutes for this. And not much time left. So that was all for the flight controls tonight. So I'm gonna grab here. We have the overhead upper panel. You can see here we have the hydraulic fluid flight control. You can disconnect with hydraulic fluid. Some other APU maintenance for the ground issues. The circuit breakers in the overhead panel. You can see the systems like landing gear, left engine over here. You can reset some systems in the overhead panel. So this is the aft. This is the forward overhead panel. I need to show you so you have a general view of the cockpit again. Maybe more nice broad view over here. As you can see, you have the same flight controls again, and the autopilot here. So you can start the APU like this over here to start make the engine start demonstration. We have the battery on already. I'm gonna turn off the engine later. So we have the ADU here, the air data and also reference unit that controls the air data, the laser gyroscopes, the position, the aircraft and the altitude, and also the magnetic heading and compass, magnetic north pole to north pole, the rate of climb and descent, the pitot static and pitot dynamic, all the displays of the air data here. We have the primary flight control computers, thrust asymmetry, compensator on and off. I think we have start the APU like this. The left engine, right engine, IDGs, the grid generators, backup generators. We have here passenger oxygen, ground proximity, window heat, emergency lights. So we have, we can turn off, this is hydraulic pumps. You can see we can turn off the hydraulic pumps like this. You will see some messages coming up here, the fold like this. We're gonna have here the display of all the systems. I'm gonna fold like the stabilizer with red is lost right now, hydraulic pressure system, the flaps here, no auto lamp spoilers, so the speed brakes. So we have hydraulic pressure system loss CR and left, so we lose some hydraulic and some flight controls. So we need to rearm in the on position all the hydraulic pumps, left engine, right engine, and C1, C2. You can see the air pressurization. We have them back to the auto when it's on. Here is the lighting system of the aircraft, windshield wipers. So this is the ram air turbine extend. We will use hydraulic pumps and engines, cargo fire arm for. Also, we have electronic engine control for the engines. Start, auto start system on and off like this. So we can use the auto start for the engine on and off. Maybe back to the normal. You can arm the fuel tank like this, select the nozzle also. Here is the crossfit valves, the fuel tank, left wing, right wing, center tank, and we're gonna see later what they do. In the display we have the ADIs on, auto off. We have also, we're gonna turn on here, we have the cabin pressurization system, the outflow to the auto now is in the manual. When we climb, we open and close the outflow valve, or we descend to increase or decrease the cabin pressure and select landing altitude. Now it's in the auto. We have here is the bleeder from the left right engine, and this is the APU we need for starting the engines, the isolation, also valves closed. So we're gonna have some systems failure and also the cabin pressurization failure. So you can see bleed isolation, bleed thrust asymmetry compensator fuel. So we lose also hydraulic pressure demand C1 and C2 here. We lose some hydraulic, also the cabin pressurization, the duct pressure is 0. So we have no cabin pressurization right now. So the bleeder is off, we're gonna turn on again. Also the APU and the packs. So this is for air conditioning and hydraulic pressurization, for wing engine at the ice, and for starting the engines, and for cabin pressurization as I told you. So we're gonna start now the engine system. We're gonna come here, CDU and AC. So we have the display here on. We're gonna have the systems on display, engine status. You can see the APU is running, the hydraulic pressure, the oxygen level over here. We have the checklist, normal menu, what we need to do before starting the engines. These items are complete, and we have the normal menu. If we have a failure, normal menu, communications, navigation, synoptics, the doors. You can see the doors of the aircraft are closed, the cabin can be pressurized, the landing gear. You can see the pressure and the temperature of the brakes, the pressure of the. Here's the electrical system, left right engine, backup generators, APU, the voltage here of the batteries. So you can see the flow of electric with green, the charger, discharge of the batteries, the hydraulic system, left engine, right engine, air pressurized, C1 and C2 electrical, side of valves. You can see where the hydraulic fluid goes, what needs, what system needs hydraulic fluid, 3000 psi each system, and the quantity of the hydraulic. Here's you can see we have fuel jettison on, so we have to disarm the fuel jettison like this. This might be more confusing, so we go back. So you can see left wing, right wing, center tank, total fuel on board, low and high pressure fuel valves, the engine symbol, center tank is empty with yellow crosses, and the forward and aft pumps, and the APU is fed from the left wing using the DC direct fuel. Also we have the air. You can see also the minimum fuel temperature here because it freezes at -37. You can see the pressurized air from the left and right engine, 59 stage. The APU also is needed for hydraulic pressurization and engine start, air conditioning. ventilation. Also, if we move the thrust levers forward, you will see the duct pressure here increases rapidly. We move them back to the idle. Now we have the last part of the flight controls. So we have, you can see the flight controls move around like this. You can see horizontal and vertical tail with the stabilizer and left and right wing. So when we move one of the flight controls go like this, up and down, you can see also the other side. So this is what it displays over here in this display. So we go back into the modes, engines. We're gonna make the engine start demonstration very quickly. We have virtual cockpit, and here we go. We turn off both engines, left and right, and we have like maybe 18 more minutes, so it's 33. You're gonna see here the engine start. Engine start on right now over here. So both engines are off. We can restart them because we have the auto start is on. You can see no fuel flow right now. It's only the to the pressurization from the APU. So we start left and right really fast. So you will see the fuel flow increase here rapidly. And here we go, have both engines, right wing and left wing. Start now very rapidly spinning, and here we can start. We can only one last step very fast. The flight management computer. We have FMC. You can see the model, the position, initialize, Lszh, the reference airport, and you have the GPS position here, the inertial reference position, the coordinates of the aircraft. Inertial, zero fuel weight, gross weight, fuel on board, calculation, reserves 5%, and cruising altitude 35,300 feet, 100% the cost index like this. You can see center of gravity. So we're gonna have the route now, Lszh, back to Lszh. Runway 14. So we have the departure, runway 14, Zwick to Alpha, arrival, Lszh 14, Negria 1 Alpha, Transamity. So we have the legs, Negria 1 Alpha, activate and execute. So we're clear. Flaps for takeoff, center of gravity, calculation, and horizontal trim stabilizer, and we have activated speed. So we only need the V-speeds, V-takeoff, V2, V-rotate. So we have the full flight plan like this. We only need now is to set the flaps for takeoff, and these are the parking brakes. And go into the runway like this. As you can see, parking brakes disarm. Use the steering here. So we have so the runway here is empty. We can use it as clear. Advance the thrust levers. Use steering wheel again. So we advance the thrust levers forward and take off. Only set the LNAV. So we're ready for takeoff. And here we go. V1, V rotate. We have the positive rate of climb. And V2, and here we go. We have the climb takeoff here. So we have a positive rate of climb like this. Pitstream a little bit down, so we track the landing gear like this. So you can see we are 2000 feet, 2400 above the ground level, but 4200 above the sea level. We climb with 5000 feet per minute. This is the terrain, the ground scanned from the radar in front of us. The navigation aids. This is the airspeed 250 knots, 210, 208. You can see the stall speed, the warning here. So we keep climbing. So we have manual flight controls now. You can see we keep climbing like this, and we have 14 more minutes for this video to end. So we keep climbing like this, steering to the waypoint. You can see we can hold neutral like this, no problem. We don't need to pitch up too much. The aircraft is very nicely balanced and climbing. You can see this is the flight plan of the aircraft route, as we call it. Now we cross 9,000 feet. We need to climb a little bit higher. So this is where we are now. Stay one more time. Let me show you the outside now view of the airplane as we climb here the Zurich. So we have a nicer view here. You can see also the galaxies here. So we keep climbing. I'm gonna show you now a nice view of the aircraft. Like this. The Boeing 777. Hope you like its wings. So now I'm gonna show you the view around. As you can see, now we have to stay back into the flight plan over here. Also, you can see we're steering manually, and we have 12 more minutes for this flight to go, for this video actually to end, because we only have 1 hour 18 minutes 50 seconds of video record time for this 4 gigabytes. You can see the Mach is 0.46, 237 knots, 16,000 feet, 2,500. So we keep climbing. Maybe we need to steer now in front of us. So we're gonna use the next waypoint here for steering. Execute. 17,000 feet. So now 18,000. So you can see the Germany now, the France this way, Germany here. So we have the Bayern Munich here in front of us. This side is the Switzerland, the Zurich. So you can see the next waypoint we're gonna be overflying. It's 1.5 nautical miles away from us. You can see we keep climbing. 30,000 feet. Maybe 2,000 feet. You can see all the commands here. 33,000 feet. So here we have the chemtrails now in the contrails. We're 33, approaching 34,000 feet. So you have the Galaxy. This is our spacecraft for tonight. The Boeing 777-300ER, flying with about 250 meters a second or 600 kilometers an hour. So we have the Switzerland here, the Germany in front of us, the Bayern Munich, France is this way, and the Galaxy here. So you have a beautiful lake here, the St. Gallen. So now we need to go inside for the rest of the steering. 35,300, and we have reached our altitude now, 35,300 feet, and we need to be manually turn around. So we're gonna increase the airspeed now. Request over here. So our new request airspeed is this, and we retract the flap source to increase the margin. So we have the balance here for this altitude over here, and we can cross like this. So this is our spacecraft at night, the Boeing 777. As you can see, we cross here the Germany, this way the Bayern Munich, and the Bavaria, and this is Switzerland, as you can see. So we cross back into the airport. So I hope you like also the frozen vapors here as we cross. So now we fly with about 900 kilometers an hour or 300 meters a second. So we need to put this down a little bit. So we have maybe like 7 more minutes to steer back into the airport, as you can see, as we could find. So this is our spacecraft for tonight, the Boeing 777-300ER, crossing the Galaxy about now 37,900 feet, and we're gonna start descending manually into the airport. So we need to start the descent now. Also the speed brakes, and reduce the airspeed request here, and the altitude, the target altitude here, 25,000. Keep going now. 6,000 feet over here request. So we're gonna have the idle thrust here request. Also, as you can see, so now we have about 6 more minutes left for this ride. Something like it, and it's slowed down a little bit. So we fly with Mach 0.7 right now. Keep descending. So we're gonna start now descending into the final approach path over here, and make maybe a shorter turn. We need to utilize slowing down the airplane also. So we have like 5-6 more minutes left for this flight. So you can see we keep descending here. We're closer now to the airport and to the ground, so we're gonna make a nice turn. Also maybe utilize the approach, the Lszh localizer. As you can see, keep descending, wearing the approach path for landing. Also reduce the airspeed momentum. So this is how we approach to the runway. You can see we are now much closer. So 3500. We have the Lszh localizer. The runway is in front of us. We keep manual thrust over here, request and automatic, and also the yoke and the rudder pedals for steering. As you can see, manual steering controls. Also we have in front of us, we have the Lszh localizer. We need to add some thrust now. Adding some thrust, keep flying manually also, as you can see, a little bit lower now. So you may see the Lszh localizer here, what it looks like for approach, the airspeed, the stall speed, the glide path, and the localizer, and we have the runway in front of us here in the navigation display. So we need just to keep it setting, and this is our path. Περίμενε 2 λεπτά. Οκ, περίμενε 2 λεπτά τελειώνει. So this is the final approach. Όχι. The final approach. Flare. Ready? 10. Here we are. Just touchdown. Parking brakes. And reverse thrust. And here we have the full reverse thrust and the parking brakes. Just touchdown here in the runway. As you can see, we keep slowing down. So here we have here you can see the nose wheel is perfectly safe. Also the landing gear, you can see the tires here, no breakages of the tires or buckling of the wheels, so the landing gear, also the nose wheel. So the aircraft is starting up, the weight should be leveled into the runway. All the tires are normal, not like some other pilots are doing with the airplane. So we made a very nice smooth landing. So we have a little bit more time here, so you can see the runway around. You can see one more time the nose wheel here in front is perfectly normal and safe, no breakages. Also the landing gear behind it, the aircraft is standing very nice. So we're gonna use it for one more flight if we wish. So disarm the parking brakes. So that was Thomas Hatsios, the British American pilot of the United States Air Force, flying the Boeing 777-300 PR-89 flight. Thank you for watching me one more time. I'll see you in the next video. Bye bye. We just made a very nice flight and now we're back into the airport. We went for the Boeing 737. So I'll see you next time. Bye bye. You can see here. Okay.